Okay, let's get started. We only have less than half an hour, so it will be a brief introduction, very brief introduction to momentum. So we will define momentum in analogy of what we did with energy, and we will carry the concepts the same way. But for today, we will just introduce what momentum is. These are the topics that we will cover in class this week. We will cover momentum, impulse momentum theorem, which is equivalent to work energy theorem, and then conservation of momentum, which is also equivalent to conservation of, not equivalent, is analogous to conservation of energy. Then, if we have enough time, we will talk a little bit about collisions, and we will give some examples of biological collisions. This week we have a lab. We have a lab that combines both energy and momentum. I still didn't write it. I don't know what it will be, but there should be a lab on Wednesday. Also, I haven't uploaded the homework today. I haven't written it down, so when I upload it, it will probably be tomorrow. Then the deadline will not be on Friday. It will be a day after, because I uploaded the day after. Okay. So momentum. Momentum is so central to motion. In fact, momentum is motion, or at least this is the origin of the word. So the word momentum itself comes from the Latin origin movimentum. This part is for motion or movement, and this part is just a suffix that makes the verb a noun. So, and this is the same root for the word movement. So the word momentum, in fact, is motion, and this is the sense in which Isaac Newton himself used the word. When he developed the famous law, Newton's second law, he developed it in terms of momentum, not in terms of mass and acceleration as we did. And he called it quantity of motion. So how do we quantify motion? So we talked about kinematics. We talked about velocity, position, acceleration, and all that good stuff. But if we want to pick a quantity that quantifies like how much motion an object has, we cannot, for example, take velocity alone by itself or speed, because if you have like a ball moving at 5 meters per second, and this ball is 10 grams, 10-gram ball moving with 5 meters per second, and you have a heavy truck moving with the same 5 meters per second, and it has mass, let's say 2,500 kilograms, then they don't have the same characteristics of motion. Like they're moving with the same speed, but intuitively we know they're not the same. Like you would rather be hit by the ball and not with the truck, of course. So we need another quantity that distinguish this aspect of motion, okay? And of course, what comes to mind is mass, because mass is what quantifies the heaviness of an object. So we can combine, so instead of velocity, we can combine, for example, mass times speed, and that will differentiate between those two quantities. So if we multiply the mass times speed here for the small ball, we will get 0.01 kilograms times 5 meters per second. That will give us 0.05 kilogram meter per second. And for the truck, we will get a very big number that matches our intuition of how heavy the truck is. So this is about this amount. But this is still not enough, because we could have another truck moving in the opposite direction and with the same speed. And we want to have something that differentiate between both. Because if we didn't differentiate between both, then this quantity will be no more than another form of kinetic energy, for example. Because kinetic energy had a measure of speed and mass in it, so it quantifies motion pretty well, except for direction. So we need a quantity that defines direction, and that's why we use velocity and not speed. Okay? So we define momentum in this way. So this was just motivation. So momentum, we denote it with the symbol B, P with an arrow on it on top because it's a vector. And we define it as the mass times the velocity of an object. If an object has mass m and is moving with velocity v, then the momentum of this object is m times v. Okay? Of course, momentum is a vector. It's a vector quantity. It has both magnitude and direction, and this is because velocity itself is a vector. And it has units of mass times velocity, or SI units, which is kilogram meters per second. Okay. Newton's second law, as we said, was originally developed in terms of momentum, not in terms of mass and acceleration. And it was written down on this form. Force is equal to change of momentum over change in time. Okay. In that sense, force causes change in motion because motion in that sense is just momentum. So force causes change of motion. Okay. And this form is equivalent to the form we had, but it has more information because it's more general. So let's check that this gives us the same formula that we know for Newton's law, which is F equals ma. Let's check that we get that again. So we have F equals delta P over delta T, and delta, as we know, is just final minus initial over delta T. And from the definition of momentum that we had above, we had mass final, velocity final, minus mass initial, velocity initial over delta T. Yes.
It's just lagging a little bit. You're good. Maybe you're good.
Yeah. Okay. Yeah, I'm sorry, I have no control on this. Okay, so we have the formula so far for the force on the left-hand side, and on the right-hand side, we're trying to get it to the form we know for momentum. Oh, okay. Isn't. Okay. If the mass is the same before and after, let's assume the final mass is equal to initial mass, which we denote both by the symbol m without any subscripts. We get force equal to m. We can take m as a common factor, v final minus v initial over delta t, or just m delta v over delta t. We know this is the definition of acceleration. So this is m times a. which is the same form we know for Newton's second law. But we had to assume that the masses are the same, initial and final. And this is not in general true. For example, if you have a rocket, mass does change because the rocket ejects some of its mass to get a thrust, okay? So mass is not in general constant, and whenever it's not constant, we cannot use F equals ma. We have to use the general form, which is F equals change in P over change in T, okay? And this is how the law was originally written in, to start with. So, okay, so now we have momentum, we defined momentum, and I want to make an analogy with the energy model that we had last week. So in the energy model, we had objects in a system. These objects have energy, like kinetic energy and interaction energies between them in the form of potential energy, spring energy, thermal energy. And those energies could transform among themselves. And the total energy was the sum of individual energies. Right? And we said that energy could be transferred into the system or out of the system by doing work on the system. So work is done to transfer energy. And work is done to transfer energy only by external forces from the environment on the system. On the other hand, these objects in the system also have momentum. So they have masses and they're moving, interacting with each other. So let's say this object has some velocity v1 and has mass m1. This object has mass m2 and moving with another velocity v2. This object is going this way, v3, m3, and so forth. So all of these have momenta, p1, p2, and p3. So I can actually denote them p1, p2, and p3. And you know, p is just equal to mv, mass times velocity. In the same way, momentum can also be transferred into the system or out of the system by impulse. Okay. Impulse can transfer momentum. And inside the system, momentum can be transformed from one object to the other. Like one object can hit the other, give it some of its momentum, and then lose some momentum itself. So momenta inside the system can be transformed among themselves. And from an external force, you can have an impulse that changes the total momentum of the system. And the total momentum we denoted by a capital P vector. It's equal to the sum of all individual momenta. Just in the same way that energy was the sum of individual energies of the system, momentum, total momentum is also the sum of all individual momenta. Internal forces only cause changes in momentum within the system, the same way internal forces cause transformations of energy. And external forces can change the total momentum. Okay. For energy, we had this cause and effect relationship that if you have work acting on a system, you get change in energy. This was the cause and this was the effect. Similarly, for momentum, we have the impulse momentum theorem, which says impulse, we denote it by J, causes change in momentum, total momentum. Okay. Also, this is the cause, and this is the effect. Then we defined work, a mathematical definition saying that work is equal to force times displacement. There was an angle, but just for comparison, let's assume it's just F times distance, like force times distance. And this was a definition. We will do the same thing for impulse. We will define it as force times time. This is also a definition. So work was a force acting over a distance. Impulse is a force acting over a time interval. And this impulse changes the momentum of the system. So impulse causes change in momentum, work causes change of energy, and both of them come from the fact that F changes momentum in the first place. So this was the cause and this was the effect. And we just, sometime we multiplied by distance, sometime we multiplied by time, but the fundamental relation is Newton's second law, from which we derive all of these other derived quantities to help us understand the physics better. But the fundamental relation is Newton's second law. Okay. We will go over all of this in detail tomorrow, but I'm just covering the concepts like intuitively or conceptually today. Continuing our analogy, we used this equation to say if we have an isolated system defined by the fact that there is no external force acting on the system, then energy is conserved. The change in energy is zero. The change of the total energy of the system is zero. Here we do the same thing. If the system is isolated, which also means F net is equal to zero, which implies that J itself is equal to zero because J is just F net times time, and time is just a number. We get conservation of momentum, which is the change in the total momentum is equal to zero. This was conservation of energy. And this is conservation of momentum. In conservation of energy problems, we had energies transform among themselves, but the total energy had to be constant. Same here, we will have momenta exchanging between particles among themselves, but the total momentum of the system is a constant number or a constant vector. Okay. This is the model. It's basically an analogy with the work and energy. We will do everything analogously. And we will have some problems on collisions to apply the concept of conservation of momentum and see how momentum is transformed. And then we will give some applications from biology. Okay. I don't think I can cover any content today more than what I already did because we only have 5 more minutes. So I will just leave it there and we will discuss the topic in detail tomorrow. Okay?